Hello, 大家好，我是 Edmund, and welcome back to Edmund's Maths. Now, in this video, everything which I write on the board is correct. Regretfully, there are a few things which are unfortunately incorrect. These are corrected in the video, also in the description and comments. So I apologise for that, and I look forward to this next video. Let's get on with it. Welcome back to another video. Now, in the last video, we actually found the analytical solutions of the problem of two masses coming together with no external forces. Now, you might think, what's the point in doing all that analysis? I mean, can't we just put the equations of motion into a computer and just plot the solutions on a graph and say, hey ho, we can find the values of these x1 and x2 at every position of time because our computer will solve it. Well, I have two things to say to that. The first being that actually solving the equations of motion and going through all this derivation is quite fun. And the second point I'd argue is that you can actually get more analysis of the limiting behaviour of the functions with time for certain values of time with the analytical solution, which is something we're going to be doing more in the next video. But for this video, I want to prove to you that actually you can get some sense out of these analytical solutions. You know, they're not that ugly, so let's give them a go. So remember that our x1 of t, so the value of the position of the first mass as a function of time, we derived as a times m2 over m1 plus m2 times the inverse incomplete beta function half 3 over 2 of kappa times time, where kappa is this constant here, which is 2 times the gravitational constant times by m1 plus m2 divided by a cubed, the square root of which. And, well, how are we going to plot this? Well, we know what the inverse incomplete beta function looks like. Remember, I did that in another video. The inverse incomplete beta function, I'm just going to call it beta to the minus 1. We know that it's actually this thing. Well, I'll put the half 3 over 2 here, you know, and kappa t. Why not? The graph of this, if you remember, is something that looks like this, where kappa t, when kappa times t reaches pi by 2, then the inverse incomplete beta function, this thing, will reach 1. Now, let's therefore plot this thing. Because x1 of t is just this multiplied by this constant, so we know it will be the same shape. So let's draw this, and we've got the position here. This is our kappa times time, and we can now just go ahead. We know that the graph will be the same shape because it's a constant, and we know that because the arguments of these functions are the same, we know that when this thing reaches pi by 2, this is actually the last point on our graph, and actually we know that because if you remember from the last video, when kappa t is equal to pi by 2, that is actually when the masses will have collided and come together, and that's when the motion will finish. So we only need to worry about the values between in this domain of kappa times t. So what happens when kappa t is equal to pi by 2? Well, we know that this thing will be 1, so this x1 will actually be equal to this constant. So this will be equal to a times m1 over m1 plus m2. And we can go ahead now and sketch this as the same shape. Then the gradient will be infinite here and be 0 here. Okay, so that's our x1 as a function of time. I don't like the way I've written the x there. There we go, that looks a bit nicer. So what's there left to do now? Well, we've still got the position of the x2 to sketch. So x2 of t, if you recall, was equal to a times 1 minus m2 over m1 plus m2 times by the inverse incomplete beta function, blah, blah, blah again. Now in this case, we know that the shape of the x2 position will be 1 minus this thing. We know that 1 minus a constant smaller than 1 of this graph. Now we know that if we did this graph, if we did 1 minus the inverse incomplete beta function, we know that we'd get a graph like this. But because this constant here, this m2 over m1 plus m2, we know that that is less than 1 because m1 plus m2 is greater than m2. We know that therefore this function will never quite reach the x-axis. So we actually know that it will do something more like this sort of thing. Okay, but what we really want to know is what is this value in this case. So we know what the shape is, we know what the general sort of function looks like, but we now got to pay our attention to x2 of t. So we know that x2, the best thing we can do when we're drawing graphs of functions is try and find specific points. So we know that when t is 0, that's when you plug 0 into here. In this case, this whole thing will be 0 because the inverse incomplete beta function is 0, 0. So we just end up with a on its own. So x2 of 0 is a. Actually, that was the initial condition of the problem, so that better bloody well be true because we solved our equations assuming this is true. And indeed, that was our initial condition. So brilliant. So x2 when t is 0 will be just a. And we know that a is larger than that thing because this thing, m1 over m1 plus m2, is actually less than 1. So this will actually be less than this. And we know the shape will be like that. Well, what about the value when we get to pi by 2? Well, what we have to do is, if we shove in kappa t, now this kappa t is being equal to pi by 2. So let's shove in pi by 2 here. Now remember, we worked out in this second video, we worked out the incomplete beta function at 1 is equal to pi by 2. So the inverse of the incomplete beta function at pi by 2 we know is 1. So we know that x2 of t, big T, we know that that's the time of collision, is equal to this thing right here. And if you simplify this algebra, I'm not going to do it in this video, I think you're all good enough to do this yourself. We know that this will actually, when you simplify it, be equal to m1 over m1 plus m2. So, that's actually this value here. So we can now go ahead and plot this, sorry, not plot, we can go ahead and sketch this graph. We're not a computer, we're better than that. So we've now sketched this graph and, does this thing actually make sense? Well, okay, so the position, what this graph is actually saying is that the position of the first mass is going up with time. Does that make sense? Well, indeed, physically, the position of the mass is increasing with time. And you can see that the slope is actually getting greater. Does that make sense? Well, the slope getting greater is just saying that the velocity is increasing with time, which also makes sense because the particle is going to accelerate towards the other mass. With x2, we know that it starts at some position A, and the position on the x-axis of the second mass is continuously decreasing from this graph. And does that actually happen in real life? Well, indeed, our physical intuition says that indeed this second mass will actually get, the coordinate of the second mass will actually decrease with time. So again, this graph also makes sense. We know that the particles will collide at some point, and at this point, the positions will be the same. And that will be the time when kappa t is pi by 2. That will be when t is equal to big T, and that will be the time when it collides. So that will make sense. That's jolly good. So that's great because we've managed to find some of the behaviour of these masses. You know, if we didn't know this physical picture, and we were just presented with the analytical solutions to the equations of motion, we would be able to kind of unearth what the particles actually do, which shows our analytical solution actually makes some sense. So let's go ahead now, and because of course we haven't finished yet, last video we also derived the velocities, so let's plot the velocities and see that hopefully they make some physical sense. Now we can plot the velocities. Now if you recall, the velocity x1 of t dot is given by a times m1, sorry no it was m2, m1 plus m2 times kappa times the inverse incomplete beta function, half 3 over 2 of kappa times time divided by 1 minus beta inverse incomplete beta function, half 3 over 2 of kappa times time, all taken to the power of a half. This looks absolutely awful. I mean, how are we going to sketch this? Well, this is going to take some real work. Now, we can actually think about how we're going to do this. Now, the best way is probably to look at the most complicated thing first. So the most complicated part is this 1 over inverse incomplete beta function to the power of a half. So what we can do is just start with the inverse incomplete beta function. Now, I'm actually going to just relabel this. Rather than having all this junk on here, I'm just going to relabel this beta inverse and beta inverse, because this just looks a lot nicer than all that other stuff. What I'm also going to do is I'm going to take away this constant. I know that all this stuff at the front is just a constant. I'm just going to relabel it A. Yeah, this now looks a lot nicer to deal with. So as long as we can sketch this form, then we can sketch this. So we can first of all look at what the inverse incomplete beta function looks like. So we know that inverse incomplete beta function goes from 0 to pi by 2 and it reaches the value 1, and it does this. Now what we can do now is think about what 1 minus this will be. So 1 minus this thing will just be, well, we're basically adding 1 and then doing the minus of it. So we're doing the minus of it, adding 1. This will make a graph looking like this. Okay, now the next step. This has like a 1 over 1 minus beta inverse. So we can just take the inverse of this. And the inverse of this graph, well, we know that if you take any number less than 1, if you take the reciprocal of it, it will actually get bigger. So we know that 1 over will actually get larger and larger. And as this approaches 0, 1 over this will asymptote towards infinity. So this will actually asymptote towards infinity, and the asymptote line will be x equal to pi by 2. Okay, so what will this taken to the power of minus a half be? And that deals with this whole thing here in this graph. So once we know this, we're much well on our way of finding the form of this function. So if you take the square root of this, well, the square root of any number that's greater than 1 is still a positive number greater than 1. So actually the form of this graph won't change. Of course, the actual values will change, but the shape of the graph won't change. Okay, so the last thing to do now is basically this function, all this function actually is just some constant a times by the inverse incomplete beta function taken to the power of a half times by 1 minus the inverse incomplete beta function taken to the power of minus a half. Yeah, because I've just taken that and just multiplied it by that. So this thing, to get this thing, we just need to multiply this graph by this thing here. Now, what is that thing there? Well, we can just go ahead and plot the inverse incomplete beta function, which will be like that. And, well, when we take the square root of it, what will it do? Well, I'm going to sort of fudge it here and say, you know, look, I'm not going to really care about the curvature, if the curvature might change or not, because actually I'm only going to worry about the curvature after we've multiplied those functions together. So actually I'm just going to go ahead and essentially multiply these two graphs, and that will get what this thing looks like. So let's think about this. When you multiply these two lines, what is the resulting function going to be? Well, if you multiply 1 by 0, then you get 0, so it still starts at 0. And pretty much you're going to get a line where every value just goes in between those two values. So this middle line here is actually equal to this, which is actually the function, the value of this. So we know that the x1 dot of t will actually be this will actually have the shape of this graph. So we know that if we plot now x1 dot of t, let's call this x dot, we will get a graph that looks like this. So if this is pi by 2, we will get a graph that looks something like this. Where as capital T tends towards pi by 2, the graph will actually shoot up towards infinity. Now, this is our x1 dot of t. And does this make physical sense? Well, what this graph is saying is the velocity is increasing as time is increasing. And does that work for our real particles? Well, of course, as the particle moves, it is accelerating towards the other mass, so the acceleration is positive. So indeed, the velocity increases, but the rate of change of velocity is also increasing because this graph has positive curvature. So that implies that the acceleration is also increasing with time. Does that make sense? Well, remember these particles are getting closer together, so the force of gravitation from the other mass is also increasing. So we do expect the acceleration to be increasing, so therefore we do accept this. We do expect a line that looks like that. Now the next thing that looks a bit dodgy is, well, the speed tends to infinity as kappa T tends to a finite value, which should never happen in physics. Oh dear, well, why does that happen? Well, we can explain that because the gravitational potential between these two masses, the gravitational potential energy, is actually a inverse relationship. And actually, it will, therefore, when the separation of the masses tends to zero, the gravitational potential energy will tend to will diverge. Therefore, the kinetic energy will also diverge. That's why you get this diverging velocity. But why does that happen? That shouldn't happen in a physical problem. Let's think. Why does it do that? Well, I know. Remember, this model was assuming that these are just point masses. And of course, when the centers of masses actually touch, this is what this picture is saying. However, in real life, of course, when two particles come together, their centers of masses don't touch. Their centers of masses actually don't meet. So this model hasn't taken into account the finite size. Now you can take into account the finite size because we know what these exact trajectories are. You know the exact positions, so you can kind of stop the motion when it does that. But in reality, of course, there will be some cutoff value of the velocity where the masses don't quite meet because the centers of masses don't quite touch. They're stopped by the finite size of the particles. So that's something that could be modified in the model. Okay, so that's good. That saved us. Okay, what about the second mass? Well, we know from the previous video that the second mass's velocity is given by this equation. And that just means that the second mass will just have a form that looks like this. Because it's just the negative of the first one, multiplied by some constant, but again, we don't really care about it because we're only really interested in the form. And because there's no interesting points here apart from infinity and zero, so we don't really need to worry about the constant and those kind of things. So, okay, and again, this makes sense because the velocity is of course negative because it's moving down the negative x-axis, and indeed, it tends to minus infinity for the same reason, of course. But in real life, it wouldn't do that, and this model also wouldn't do that if you took into account the finite size of the particles. Brilliant. So, well, I've shown that if you start with the bare analytical solutions and actually know nothing about this problem, then you can actually get meaningful physical results from the analytical solution that we got from the equations of motion, which is absolutely fantastic. And even more fantastic is the fact that we actually got something which made intuitive sense, which actually kind of gives us more confidence that our analytical solutions were perhaps correct. So thank you for watching, and join me in the next video when we're going to do some limiting cases of this.